Can you hear me in the back there? Okay. Okay guys, it's 4:15, so let's get started then. So welcome to the second meeting of this course. I'm Minesh, and I'm one of Professor Mutlu's PhD students. And unfortunately, he's not here today, so I'll be giving some example reviews just to, give you a taste of what a review should potentially look like, right? Okay, so let's get started. So I hope this looks familiar to you guys from the last meeting. And so this is sort of the general structure we expect from your presentation, right? So we have about 25 minutes of summary of the technical content of your paper. And then we expect about 10 minutes of critique, including strengths and weaknesses that you identify in this work. And then 10 minutes of discussion, which both includes new ideas and problems that you identify, and also an open brainstorming and discussion period for interactive between the audience and yourself, right? So I'll give an example today, and you can see how all these different structures come up. So just a quick note on course logistics. So the requirements as of right now are to first submit homework 0, which is on the course website, and it's due tomorrow at midnight. So please go ahead and do that. And the second requirement is to choose your paper preferences by the 2nd of March at midnight. And this one's especially important because based on your paper preferences, we'll go ahead and assign you the papers that you choose essentially. And we'll go ahead and schedule the semester. And so throughout the semester, we expect 2 presentations in each meeting, and we'll have 11 sessions total. And for each session, each presentation should be a maximum of about 50 minutes, and this includes the question and answer session, right? And in each session, we expect to take the entire 2 hours, so don't plan on this lecture ending early or anything. For each of the presentations that you do, basically one student will present one paper and then lead the discussion about the paper. And then we'll have a maximum of about 25 minutes, just sort of a summary and analysis of the technical content, and then 20 minutes of critique, discussion, brainstorming, and feedback, right? And so this leaves about 5 minutes margin for this 50-minute period, depending, how the timing works out for each of these. One thing to note is that, you should generally follow the suggested guidelines, but as Professor Mutlu talked about last week, this isn't necessarily a hard requirement, right? I mean, so the suggested guidelines are a way for you to be sure that your presentation will be pretty good. But if you want to sort of break free from those guidelines, you can. And with the help of the mentors that you meet with throughout the semester, you can sort of flesh out a new design that's sort of how you want to present the paper. Okay, any questions about that? Okay, so Professor Mutlu sort of put together this general algorithm for presenting a paper, right? And so first, it's start with studying lecture 1 again, just for the general presentation guidelines, right? And so this is sort of how you should sort of organize your presentation. Then make sure that you read and analyze your paper thoroughly, right? So you need to make sure that you understand what this paper is presenting, what it includes, and potentially related work in the area, right? Because since you're expected to lead a discussion about this, you don't need to be an expert necessarily in the subject matter, but you do need to be able to lead this discussion. And the TAs will sort of be in the crowd to sort of help you with that as well if something super technical comes up. But make sure you understand what you're talking about. In order to do this, you can discuss with anybody you want. This includes any of the TAs or using any online resources, the ETH library or what have you. Just go ahead and make sure you know what's going on. And then you can prepare a presentation draft based on our guidelines or however you see fit, right? And so once you go ahead and do this, meet with your mentor and get feedback about what you put together. And so typically this type of meeting is essentially a practice presentation, right? So you'll meet with one of us, one of the TAs, and then you'll sort of go through the draft that you prepared as if this was the real presentation, right? And then we'll give you feedback about what you could potentially change, what else you should include, which parts need a little bit of work, which parts are good. And then you should sort of revise the presentation and your delivery based on this feedback, right? So after you go ahead and do this, hopefully your draft is getting more and more fleshed out. Then you should meet with your mentors again and get more feedback, right? So you can improve this even further. And probably after you get your first round of feedback and you make your improvements, there's new things that will come up, right? Or you can improve this even more. And so go ahead and revise the presentation based on the second meeting. And so in this course, we're requiring you to meet with the mentors twice. However, if you want to, flesh it out even further, you can meet more times. Just sort of communicate with your mentors via email to, see whatever timings work out. And so these 2 meetings are mandatory, and you need to schedule them with your assigned mentors, right? So for each paper, so for each of you, typically we assign 2 mentors. And so it's just sort of figure out meeting times that will work. And, we might suggest meeting times that are good for us, and we just go from there, right? And the last thing is to make sure that you practice, right? Practice your delivery and everything. So Professor Mutlu last week talked about how, one good strategy for practicing is to present to yourself in the mirror, right? And so this sort of helps you both to get an idea of how you're presenting on stage, right? So if you're walking around too much or you appear nervous and do something strange, maybe you'll catch that and you can avoid doing that during the real presentation. But also it sort of simulates presenting to a real audience as opposed to just presenting to a wall. And as people's expressions changes and they have questions and stuff, it might throw you off. So especially if you're not so experienced with giving presentations to several people, this might be a good way to do it, right? So yes, practice, practice, practice. Okay, so do you have any questions about that? Otherwise, I'll jump into the example paper presentations. Yes?
So last week you said the week after this week, also like next week, the presentation, like from the students are going to start. But like the sign up for the papers closes on like Monday, so I guess we will not know till Monday what papers are, and it's kind of a short time from Monday to Thursday.
Yes, that's a very good point. Mohammed, are we having lectures next week, or are the students?
So basically you'll start, guys, presenting on March 19th. This is the first session. So you have 2 weeks to prepare if you are the first guy.
Okay, sounds good, yes.
Regarding the matching of personal paper, is it first come, first serve, or?
Yeah, so there are some papers that might be more popular or more flashy or something, and several people will try and sign up for that. So basically from each of you, we'll have an ordered list of which papers you prefer, right? And I guess I'm not sure what algorithm you use for matching those to students, but you may or may not get your first choice, right? I'm not exactly sure more than that. I don't know, do you have anything to add?
So we'll make sure that you got the highest ranked paper assigned to you. We will be sure that will happen. But at least you should rank 8 papers as top, and we will make sure one of them will get assigned to you.
Okay. Does that, yeah, sounds good. Okay.
There's around 60 papers in the list, so we assume the collision will be reduced, hopefully.
Yeah, so when you're going to make your list of preferences, you probably won't be able to read all these papers or whatever, but you can at least make sure to go through the abstracts and make sure that they're things that you're sort of interested in at least, just because you don't want to be stuck presenting something that just doesn't work for you, right? Yeah. Okay, anything else before we move on? Okay, perfect. So I'm going to start off by giving an example paper presentation. And the theory behind this is that it's sort of an example that you can learn from, right? And as Professor Mutlu again said last week, learning by example is an excellent way of learning. And we'll do at least one presentation today. If we get time after the break, hopefully I can go into a second presentation as well. If not, then both of these examples will be online and we'll post them on the course website, so you can go ahead and take a look at them. And if nothing else, the lecture videos from previous years are actually also online under Professor Mutlu's channel. So, if you want even more examples, basically, you can go ahead and look at those. All right. So here's this slide on the structure of the presentation, and we've seen this several times now. I'm not going to go through it again, but essentially what you can expect is that throughout the presentation, we'll see each of these different headings come up, right? And these will sort of be different segments of the presentation, right? So I'll start out talking about, background, problem, and goal, and you'll see this exact slide come up, and then I'll talk about it. Then we have, novelty, key approach and ideas, so forth. We go through all these different sections. We have the results, the summary. Right, so with this part, with the summary, we sort of end the technical content. And so this is, before the summary, it's sort of just presenting what's contained in the paper. And everything after the summary is sort of your interpretation. And so we get into sort of the analysis and discussion, right? And in this section, we're looking at what your analysis is like, right? So it's how you want to put it together. So for the analysis, we start off with, talking about the strengths of the paper that you believe are strengths, weaknesses that you identify, and your thoughts and ideas about the paper. Right, so your thoughts and ideas sort of means, what you think could be done better, what are follow-up works to this paper, where you see opportunities, things like this, right? And you'll see in the example what I mean by this. Then takeaways, and so here, these takeaways are a little bit different than the summary from before, right? So the takeaways should be what you think are the most important aspects of this work, and they sort of lead into the open discussion afterwards. So there's no right or wrong answer necessarily, and you can, talk about these with your mentor when you meet with them, sort of get ideas as to what you could put. But it's essentially your interpretation. And then we lead into the open discussion. So we typically expect you to have some types of discussion starters. So this is an open discussion with the audience. And so I should have sort of these discussion starters that I've been thinking about as I was preparing this presentation. right? So when students ask questions, I can point to related works maybe. I can talk about some other ways people have done things. Just sort of have a little bit of understanding of the area, right? And be ready to hold this discussion. And we expect the discussion to be about 10 minutes or so. Okay. Yeah, so any questions about that? Otherwise, now I'll actually get into the example presentation. Yes?
So you talked about older years presentations being online.
Yes.
Are we being recorded during our presentation?
No. So the example lectures given by the TAs are online. So Professor Mutlu and I think myself, maybe one of the other students in the past as well. So the several past years, those are publicly on YouTube. However, your lectures will not be publicly posted, right? So I believe we'll be recording the lectures, but they're only for you, just to internally look back at presentations in the past. So at the end of the course, you'll sort of have to fill in a report. And here it's good to reference the presentation that you gave before, because you'll sort of write a little bit more about the paper you did. It's just a write-up version of the talk, essentially, answering some basic questions and things. However, those will not be publicly available in any way. So there's no need to worry about that. I think we'll make more announcements about this later, right? So that'll be a little more clear too. Does that make sense? Okay. Yeah, sounds good. So today I'm going to talk about this paper. And it's a paper by a student in Professor Mutlu's group, right? So this is a PhD student called Vivek, who graduated several years ago. And so this paper was presented in a conference called Micro, which deals with ideas in microarchitecture. And it was presented in 2013, right? And so the paper is called RowClone, fast and energy efficient in DRAM bulk data copy and initialization. And for some of you who took Professor Mutlu's courses in the past, right, this might look a little bit familiar. And so I'm going to go through essentially what was a conference talk and provide the technical content, and then give an example of what the discussion and Q&A and all of that might look like, right? Okay. So this is the title slide from the talk. And so, yeah, as I said, it was originally presented at Micro 2013, and today's presenter is myself, Minesh, right? And so this work was originally done as a collaboration between Carnegie Mellon University and Intel Corporation. So I'm going to start off with the background problem and goal, right? So here's what a typical system sort of looks like, right? We have multiple cores inside a CPU, and there's some sort of caching hierarchy, and then there's a memory controller which connects the CPU die with memory, right? And this is typically an off-chip interconnect. So in our work, we want to focus on this off-chip interconnect, right? And so this has several problems. So first, it provides a limited bandwidth because there's only so much data you can transfer per unit time. And it also consumes a significant amount of energy, right? Because you're moving data back and forth on a potentially pretty long bus. So our goal in this work is to somehow reduce the memory bandwidth demand here, right? And so what we want to do is we want to essentially reduce unnecessary data movement across this bus, right? And so two key use cases of copying data across this bus is a bulk data copy and bulk data initialization. And by this, I mean, for example, you could imagine we have a source buffer somewhere in memory, and we want to copy that entire source buffer to some other destination in memory, right? So this is just a copy operation of a large piece of data, right? It could be several virtual pages or arrays and data structures, what have you. But it's all some sort of bulk data copying. And the other example is bulk data initialization, where we're broadcasting a single value to an entire destination buffer, right? So this involves transferring a whole bunch of data to all these destination locations. And it turns out these two use cases are very common in today's systems, right? And so there's many different works that talk about this, and they're all sort of architectural trends on operating system performance. Why aren't operating systems getting fast as hardware? All these deal with sort of systems level topics, right? And they all point out that copy and initialization are big problems, right? Okay, so here are some example concrete use cases of where copy and initialization happen. Right, so first we can talk about process forking. So when an operating system forks a process, we have to copy the memory state of the original process to the child process, right? Now this might happen in a delayed fashion, right, with copy on write or some other mechanism. But eventually if the copy needs to happen, we're essentially just copy pasting a whole bunch of data, right? Another good example is zero initialization, where even for security reasons, when a process first allocates memory, we want that to be a region of zeros rather than being remnant from what the previous process had at that location, right? And so current operating systems, actually, a lot of them, when a process deallocates memory, they go ahead and zero the page so that this information is not leaked to some other process in the future, right? And so this is essentially an instance of initialization where we're broadcasting zeros to a whole bunch of memory regions. Checkpointing is another good example. It's literally just copying the state of a process and saving it for some future, for essentially a checkpoint restore, right? Virtual machine cloning and deduplication is another very important use case. And a lot of the virtual machine people care about this a lot, right? Because we have multiple virtual machines going on and they might be sharing a lot of data and we want to maybe save memory by deduplicating those. And there's all sorts of challenges that come up with virtual machines. Page migration, copying data from one place to another, right? So we're moving it, but that initially starts out with a copy. And there's many more use cases as presented in the works I just mentioned, right? So remember this paper was published in 2013, right? So Google actually had a publication in 2015, which is after this work was published. But they showed that 5% of the cycles in all of Google's data centers are actually spent on 2 standard library calls, memmove and memcopy, which essentially perform copy operations, right? And so this is really good motivation for the idea we're talking about here. And actually, these authors of this Google paper cite this RowClone paper as a potential solution to help mitigate this problem. Okay. So let's talk a bit more concretely, right? So the shortcomings of today's systems. So now we're talking about copy and initialization. I'm going to focus on copy in this example, right? So let's suppose in our memory we have a white buffer and then a gray buffer, and we want to copy the white buffer to the gray buffer, right? So in the conventional system, what we have to do is we slice up this white buffer into small pieces, and then we transfer those pieces across the memory bus, right? And so it goes across the memory bus to the memory controller, through the cache hierarchy, all the way to the CPU, right? Then we do the exact same thing with the gray buffer. Now, even if we're going to overwrite the gray buffer, in order to write to a cache line, it sort of needs to be fetched from memory and resident in the cache, right? And so we bring this buffer into memory as well, piece by piece, and then we perform the copy, right? Which essentially is just a write to the cache line. And then what we have to do is we have to flush it back, right? And so this is problematic, right? For 4 different reasons. First, it's a very high latency operation because we're transferring all of these pieces of data across the bus through the cache hierarchy all the way to the CPU, right? And instead, all we're really trying to do is just move data from one place to another in the memory, right? So you might ask why we have to transfer it all the way just to do that. A second problem is it has high bandwidth utilization, right? And if you notice, there's actually some sort of amplification effect here because we're just trying to copy one buffer. Whoops. Excuse me. We're trying to copy just one buffer. But in fact, what we have to do is we have to bring the entire buffer here, bring the second buffer here, and then move everything back, right? So we actually get 3 times the number of data across this bus, as opposed to just copying this buffer across once. Sorry, I skipped ahead, it seems. Okay, here we go. Third, it also introduces some cache pollution. And this is because we're bringing all this data into the cache, even though we might not be using it straight away. Right, so if we're just doing this copy and later on in the application we're actually going to modify this data, we don't need to bring it to the cache already, right? Because we'll end up just evicting it essentially. And anything we bring in potentially evicted other useful data, and so we end up with some cache pollution. Now a caveat about this is that in modern systems, typically you would use a direct memory access engine to do this type of copy. So inside the memory controller there'd be a DMA engine which the CPU would invoke, and it would simply do the copy operation using data without polluting the cache hierarchy at all. Right, and so this paper does consider that. But in the more general case, you could introduce cache pollution, right? And fourth, we have unnecessary data movement or unwanted data movement. Because as I said earlier, you might not want this data immediately in the caches, but you're forced to bring it. And even if we're doing the DMA style copy, we're still transferring data across the bus, right? Back and forth. And that's still not ideal, right? We don't want to be doing that. Okay. And so this paper goes ahead and evaluates the DMA use case, and for a 4 kilobyte page, it finds that we consume about, it takes about a microsecond to do this copy, and it consumes 3.6 microjoules, right? And so these are absolute numbers, but later on we'll compare them to the benefits that we get from the RowClone operation. Okay, so now I'm going to talk about the novelty and the key approach and the idea that this paper really presents, right? So the idea is called RowClone, and the idea is to do an in-memory copy, right? So previously, where we were copying this buffer by moving it to the CPU and back, what RowClone proposes is to just move this data directly inside the memory itself, right? And so this has many benefits, right? First, it's low latency, because we don't have to go through all these interconnects just to get the data there and back. Second, it has low bandwidth utilization. And actually, in this example, absolutely 0 bandwidth utilization, right? Because there's no need to transfer anything across the bus. Third, we have no cache pollution because no data needs to be transferred into the caches. And fourth, there's no unwanted data movement, right? A caveat here again is that maybe you actually did want this data in the cache, right? And maybe because you were about to operate on it as well, right? So you want it to be brought to the cache, in which case maybe you don't want to do this type of copy. And the paper actually addresses this a little bit, and we'll talk about it later in the evaluations. But in the general case, there's no unwanted data movement when you do this type of thing. And as I said earlier, the traditional way of doing this with DMA sort of costs this amount. With the RowClone operation, we reduce this 1046 nanoseconds to 90 nanoseconds, 3.6 microjoules to 0.04 microjoules, right? And this is a huge improvement, right? It's orders of magnitude improvement. And it's very significant, especially the energy numbers, right? Because, you can imagine for mobile devices and in data centers and things like this, the energy consumption sort of translates to cost, right? So this is a significant improvement using RowClone. So let's take a look at this in a little more detail. So here's what a typical DRAM subarray looks like, right? And so you can imagine this as a 2D grid of cells. And for example, here we say that it's 4 kilobytes wide, right? So there's 4 kilobytes worth of cells in each of these DRAM rows. So the subarray consists of the arrays of cells. And then we have a row buffer here, which essentially acts as a cache when we're trying to read one of these rows, right? And so when the CPU does read and write operations, it's sort of sourcing the data and writing the data to the row buffer while the row buffer is caching that row. So in order to do in DRAM row copy, we start off with an activation operation, right? And so this is how normal DRAM works. And so when we go ahead and activate a given row, it gets transferred to the row buffer, right? And so the activation operation results in this data in the row buffer being the same as what was in the activated row A, right? So now in a traditional system, we would do read and write operations and just get the data to the CPU back and forth, right? But instead, what RowClone proposes is to immediately follow this with a second activate operation. Now this, in a traditional DRAM sense, this would be an illegal operation. Like it's sort of undefined, you wouldn't do this. But RowClone's insight is based on the fact that if you do this second activate, what happens is that it, by virtue, deactivates the first row because you can only have one at a time. But what happens is that because there's already data in this row buffer, the data in the row buffer will actually overwrite the data in the second row that you've activated, resulting in the data from the first row being copied into the second row. And so we end up with a RowClone operation, right? And so this is sort of the key idea behind this process. And so, yes, so 2 consecutive activates. And the benefit here is that this comes at negligible hardware cost because all of this hardware is already there in standard commodity DRAM devices, right? All we're doing is using the commands a little bit differently from how they're in the specification. Okay, so now I've given the key idea. Let's talk about the mechanism in some amount of detail, right? So the goal here is not to cover everything that's contained in the paper, but just to get the point across about what the different mechanisms proposed are and what they do so that we can have a good discussion about it. Okay, so here's a standard DRAM chip organization. So we have a DRAM chip which contains different banks, right? So the banks are connected together with some sort of interconnect, and this interconnect leads to some I/O circuitry, which then leads to the memory channel, and the memory channel connects with the CPU and whatnot. So each bank in turn is divided into subarrays, and the subarrays are the picture I showed earlier, right, where they're divided into grids of cells. And so here's that 2D grid of cells again. Where each row is sort of accessed at a time by caching it in the row buffer. Okay, so based on this sort of organization, RowClone comes in 3 different flavors. The first flavor is intra-subarray RowClone, where we're copying inside a single subarray, right? And so we're copying a row to another row, and it's exactly what I illustrated before. And so the paper calls this fast parallel mode, or FPM. The second type of RowClone is called interbank RowClone, or also pipeline serial mode, where we're copying data from one bank in a chip to another bank. And we'll see how that works in more detail later on, but essentially we go byte by byte, transferring data from one bank to another. And the third mode is called inter-subarray RowClone, where we copy data between 2 different subarrays within the same bank. And unfortunately, there's no interconnect between the subarrays that allows us to just read from one and write to the other. And again, we'll talk about this more later, but essentially we implement this by copying first to another bank and then copying the data back, right? And yeah, I'll talk about that more later in the talk. Okay, so these are the 3 types of RowClone operations that the paper proposes, and so I'm going to talk about each of these individually. So first, we're talking about the fast parallel mode, right? So we have data in some source row, and we want to copy it to some destination row, where okay, this should be labeled DST row, but essentially the white is the destination here. And so this operates exactly like I described before. We first activate the source row, which copies the source row to the row buffer. And then second, we activate the destination row, which copies the same data to the destination, right? So it's very clear how the first operation works because it's how standard DRAM operates, right? Nothing new there. The second operation is a little bit less clear because according to the standard DRAM specification, you wouldn't be doing this. So let's take a look at how that works in a little more detail. So here we're illustrating what individual cells look like inside the subarray, right? So here we have a single source cell, which you can imagine is one cell out of the source row. And then we have a destination cell, which is a cell out of the destination row. And for purposes of this illustration, we're just going to ignore the rest of the rows, right? So here we have two cells, which are the source and destination, and we want to copy the data from the source to the destination. So each of these cells is connected via a bit line to the sense amplifier, right? Which is essentially an element of the row buffer. So if we go back to this diagram, it's essentially one column along here, right? We want to copy source to destination where this is a single sense amplifier. So the job of the sense amplifier is essentially to amplify the value in the cell, right? Because the cell stores just a little bit of charge. It's not enough for us to perform read-write operations on. The sense amplifier takes that amount of charge and amplifies it to a readable value. So when we go ahead and perform a RowClone operation, let's assume that there's a value of 1 stored in the source cell, which is encoded as the charge level in the capacitor, right? So here we're illustrating this as a fully charged cell where the voltage is VDD. In the destination cell, let's assume it holds a 0, and so there's essentially the voltage would be 0, right? Even though it's not illustrated in this diagram. And so in the idle state, before we go ahead and perform our activate, the charge on this particular bit line, the interconnect between the cells and the sense amplifier, starts out as VDD over 2. And so when we do an activate operation, what happens is that we connect this cell to the bit line. And so we end up with a charge sharing process between the cell and the bit line. And so this VDD and this VDD over 2 equalize voltages, right? So what happens is that both of them end up at VDD over 2 plus some delta, right? And the job of the sense amplifier is to take this delta and amplify it to a full VDD or a 0, right? And in this case, since this charge shifted upwards, the sense amplifier will go ahead and amplify the difference between the up here and down here. So both sides were initialized to VDD over 2. So essentially it amplifies the difference between these two so that this side ends up VDD, this side ends up 0, right? And so now what we have is that the bit line itself is at VDD, which was the original value stored in the cell, right? And because the sense amplifier is still connected to the cell at this point, the sense amplifier will go ahead and drive everything to VDD. And so even the cell that we started with will be fully charged again, right? And so this completes the activate process, right? So what we've done is we've activated the source row. Now what we do is we go ahead and activate the destination row to perform the RowClone operation, right? And so we disconnect the source cell from the bit line, and we connect the destination cell to the bit line. Now, what happens is that the sense amplifier again does its thing, but the difference is already established here, so this is already at VDD, and so the sense amplifier will simply just fill the destination cell with this value VDD. And so we've essentially had a copy operation from source to destination, right? So this example was copying a 1 to a 0, and you can convince yourself the opposite would work as well, right? The bit line would be shifted to 0 based on the first activate, and it would fill this destination cell with 0 as well. So regardless of what was in the destination, we've copied the source value to the destination value. Okay? So this is the essential reason that RowClone works. So the second flavor of RowClone that we talked about is intra-subarray, right? Sorry, I don't know why. Okay, yeah, so this is still the intra-subarray that we're talking about, which is within the same subarray. So essentially I'm just illustrating the same thing again, except this time the destination row is labeled. So we copy the source row to the row buffer by activating, and then we activate this destination row, which gets overwritten with the source row. So by the end of this process, all 3 structures hold the source row, right? So we've completed a copy operation. So using this intra-subarray copy, or also called the fast parallel mode, we get significant savings, right? So the latency of this type of copy is a factor of 11 faster than just doing it with the traditional system, like using the DMA logic. And the energy savings is a factor of 74, right? So these are excellent improvements, right? These are several, order of magnitude here, almost 2 orders of magnitude there. And all of this comes with no bandwidth consumption and very few changes to the DRAM chip itself, right? So this sort of means that it's a reasonably easy proposal to adopt realistically in an actual DRAM device, right? We don't need to drastically change the design in order to do this. Okay. So now, while that's all great, there are several constraints to this fast parallel mode. First, the location of the source and destination data, right? So in order to do this intra-subarray copy, both the source and destination need to be in the same subarray, right? If they're not, then we can't use this mode. Second, the size of the copy is an entire row. So there's no way around that without modifying the DRAM device somehow. So you copy the entire row from source to destination. And if the row is 4 kilobytes long, you're always copying 4 kilobyte pages, right? And maybe that's too much for your application. Maybe it's not enough, but that's a limitation of how this mechanism works. So now let's talk about the second type of copy proposed in this work, which is interbank. So now we're supposing that the source row is in one bank, and the destination row is in a different bank. So what we're going to do is we're going to copy data using this shared internal bus from one bank to another. And we're going to do this byte by byte in a pipelined manner, right? So let's suppose that our data is in this bank, and then we want to copy it to a destination in this bank. So essentially what we do is that the memory controller will initialize this bank to some type of read mode, and this bank into some type of write mode, and then we'll copy this data over this interconnect byte by byte in a serialized fashion with the memory controller orchestrating this copy, right? And so what we end up with is the data was copied from this bank to that bank. Now, this still has huge benefits, right? Because we're not transferring any data across the memory channel. Okay, and yeah, you can, without providing more details, I think this is pretty straightforward to understand, right? You would activate the row here, you would activate the row here, and the memory controller would orchestrate the copy, right? And so what we're doing here is we're overlapping the latency of the read and write operations. And so in the end, the benefits are significant, right? We have almost 2x latency reduction and over 3x energy reduction. And while these numbers are smaller than the fast parallel mode, they're still very significant, right? We're looking at, a 2x, 3x improvements. Okay. So now let's just take a look at the high-level picture here, right? So we have 3 types of RowClone operations. The first one we talked about was intra-subarray, where we just do 2 activations to copy from the source to the destination row. The second type we considered was inter-bank copy, where we copy data in a pipeline manner from one bank to another. The third type of RowClone is inter-subarray, right? Where we're copying between subarrays within the same bank. And the problem here was that there's no interconnect for us to just copy from one subarray to another. So what we actually have to do is we have to use inter-bank copy twice, right? Where we copy the data from this bank to some other bank and then copy it back. Except when we copy it back, it goes to the destination subarray instead. And as we'll see a little bit later, while this doesn't seem great, it doesn't really provide latency improvements over using a traditional system, but it provides significant energy improvements still. And since energy is a pretty big concern, this is still a net win. Okay. So these are the 3 key mechanisms that this paper proposes, right? And all of them come together at very low area cost, right? So the paper does an evaluation, it describes that it's less than 1%, 0.01% area cost, which is very, very small, right? Okay, so we've talked a lot about the copy operations now, and so the second use case was initialization, right? So one key thing to note is that initialization is sort of a special case of the copy, right? So one easy way to do zero initialization, which is very common in today's systems, is to just fix a row at 0 within each subarray in the DRAM, right? And what this allows us to do is whenever we need to initialize a different row to 0, we just perform a RowClone and just copy this 0 row to other rows, right? This results in a pretty small loss in capacity, but it's a non-zero loss in capacity. And while this might seem like sort of a weird sort of approach, it's actually done in a lot of ISAs today. So if you remember from your digital circuits class maybe, we used the MIPS ISA, right? So the MIPS ISA actually has an ISA register that's just a 0 register. It's the exact same thing as doing this, right? You can always just move the 0 register to some other CPU register. Here you can always RowClone the 0 row to some other row, right? So it's not very foreign, difficult to imagine. It's a very reasonable thing to ask for. Now, if we want to initialize to some value other than zeros, in order to initialize to arbitrary data, we can just initialize one row by writing to it normally, and then use that as an initializer for other rows, right? It's pretty reasonable to do, and in general, it should work for initialization, right? And so the paper evaluates the use case of zero initialization because it's by far the most common in today's operating systems. And the mechanism is exactly as described. We reserve a row in each subarray, and we always assume to use fast parallel mode, right? So you could reduce the overhead potentially by the capacity overhead by just having the 0 row in specific subarrays, and then using the other types of RowClone. But the paper just considers this this mode, right? And they find that there are significant savings in latency and energy by using the fast parallel mode as opposed to just doing a traditional initialization. Okay, and yes, at a relatively low loss in capacity. So here the paper provides some evaluations of what the latency and energy benefits of using these different types of RowClones are, right? So here on the left we show latency reduction, on the right energy reduction, and the y-axis is the factor of improvement, right? And the x-axis shows the 4 different use cases we talked about. So as we see in the first category, intra-subarray RowClone, we see that the benefits are significant, right? And so we already saw this before when we were talking about the fast parallel mode. For the interbank and inter-subarray copies, the benefits diminish somewhat, but they're still significant, right? These are still very good improvements over the baseline. And for the zero initialization, it's the numbers essentially that I just presented, and they're very good numbers, right? So by and large, doing this RowClone makes a lot of sense because it provides so much benefit, right? And all of this comes at very low cost, 0.1% increase in die area, right? So this is something we can easily tolerate. Okay. So now I'm going to talk about the system design to enable RowClone, right? So we've been talking a lot about this DRAM RowClone substrate, Right? So as it stands, it's just a mechanism for us to do things with. But to actually enable this at the application level, we have to consider the entire system stack, right? So this includes, the application itself, operating system, ISA, and the microarchitecture. And so there's many different questions that we have to answer that the paper sort of addresses, right? So one good question is, how do we communicate the occurrences of bulk copy initialization across all these layers? Right, so we're in the application, we're writing some code, and we have some buffer we want to copy or initialize. How do we communicate that, right? So, one easy way could be some sort of software API, but that would potentially require changes across this entire stack, right? And so the paper sort of talks about that a little bit. How do we ensure cache coherence? Because what we're essentially doing is we're modifying data directly in memory, and the caches inside the CPU know nothing about these changes, right? And so if there's data still sitting in the caches, but we do some RowClone operation, now these two sort of become incoherent with each other, right? And so we could run into coherence issues. And so the paper proposes a very simple mechanism to deal with this. The paper sort of suggests that anytime we want to do an in-memory operation, we just flush the data out of the caches. It's sort of sidestepping the problem a little bit, but it works, and it's sort of the same model that exists today for DMA-style copies. So it's, again, not too unreasonable. How to maximize latency and energy savings. So this is actually a very big question with this work. So the problem is, when do we want to do row clones or bulk initialization, and when do we just want to leave this to the CPU, right? So in order to maximize latency and energy savings, we actually want to map our data such that we're always using fast parallel mode, right? Because if we just scatter data randomly around the DRAM, we might end up having to use one of these other row clone modes that don't provide so much benefit. So this becomes a big question about mapping data in the operating system, at the application level, these different layers of address translation in the system. How do we actually make use of this? So even if it works, right, if we don't have our data mapped correctly, we can't make use of it, so it's sort of not a useful proposal, right? So all of these challenges sort of need to be addressed in order to enable RowClone. And the paper is very good in the sense that it's aware of these challenges, and it proposes simple ways to tackle these. But again, a lot of these are separate problems entirely, which are just sort of their own research area. And it's hard to do these justice in just one work, right? Another question, how to handle data reuse, right? I sort of touched upon this, right? Do we want the CPU to do the RowClone, to do the copy operation, or do we want to do it with RowClone? Because if we're about to use the data right after we do the copy, maybe we just want the CPU to do it. And the paper looks at this, and they actually analyze these two cases, right? And they find that performance can actually degrade if you do RowClone operations when you actually need the data in the CPU. So it's not good to just always offload everything to RowClone operations. So yeah, these are all important questions to answer. And so I'm going to quickly go through what the paper talks about for each of these, right? So the first is the hardware-software interface. So the paper proposes adding two new instructions to the ISA, and these are memcopy and meminit, right? These are pretty intuitive, right? They do exactly what you'd imagine them to do. And similar instructions actually already exist in today's ISAs, right? So if you consider x86, for example, there's a rep prefix you can add to most opcodes, right? Which just repeats the operation that you're going to do. So if you combine this with a move operation, you have this rep move structure, which essentially does a batch copy, right? Because you're repeating the move operation for adjacent data locations. And so you end up with sort of exactly what a memcopy would do. So these are, again, very reasonable things to propose. The microarchitectural implementation of these can be a little more complicated, right? Because the hardware itself can check whether we should do a row clone or whether we should just do this with the CPU itself, right? And so the paper proposes that the ISA can make some type of runtime decision here. If I issue a memcopy instruction, sometimes it gets offloaded to be done in the DRAM, and sometimes the CPU does it itself, right? Based on what's good based on the data layout and some other architecture visible characteristics. The second question we talked about was cache coherence. And again, so the sort of same thing I described earlier, right? RowClone's modifying data in memory, and we need to maintain the coherence of this data. And so just like DMA engines, we assume that the cache sort of flushes all this data, so the source and destination are only in memory. And the support for this already exists because of DMA, and so we can just reuse these mechanisms for RowClone, right? So it's not too much of a challenge. Again, additional optimizations are definitely possible. Like, you might not always just want to flush all of your data. Like, that's generally a very expensive process, especially if you're just going to bring it right back after the RowClone. And so maybe you want to do this at a finer granularity or something. But these are sort of beyond the scope of the paper. The third is maximizing the use of fast parallel mode, right? So this goes back to address mapping and everything. The high-level statement here is that we want to make the system software aware of where subarrays are in DRAM. Right? So actually, this doesn't happen today. Right? So from the system's perspective today, the finest granularity that the system is aware of are banks, So the system knows, well, it might be hard to figure out from the application level, but the system in general knows if an address maps to a particular bank, but it's completely oblivious to subarrays. And this can actually get very complicated because inside a bank, subarrays might not just be linearly mapped inside the subarray, right? Like address 1 goes to subarray 1 and so forth. It could actually be very complicated based on the address mapping. And so there's a whole set of challenges to try and make the operating system aware of subarrays. So that's sort of something that the paper talks about. There's also some primitives that are available for the use of fast parallel mode. So, for example, the operating system already does copy on write operations and bulk zeroing. So it's very easy to just sort of plug and play RowClone for those cases, assuming that the data is mapped acceptably. And the fourth thing we talked about was handling data reuse after zeroing, right? So this is a particular case where the paper provides a small optimization. And so what happens is that typically when we zero initialize a page, so for example, like, in phase 1, the operating system might zero out the page. And in phase 2, the application wants to use the cache lines in this page. So if we now did all of this in memory, we flushed all these cache lines, we did the zero initialization in memory, and as soon as the application wants it, it's just going to be a ton of cache misses, right? So yeah, that's what it says here, right? So RowClone, it avoids misses in phase 1 because all of this is happening inside the memory, but it incurs cache misses in phase 2 for every piece of data that the application actually wants. And so the authors address this by proposing a sort of mini mechanism here called RowClone Zero Insert, or RowClone ZI. And this essentially inserts clean zero cache lines without actually fetching this data from memory, right? And so it alleviates this specific problem where we do a zero initialization in memory and the CPU needs the data, right? Okay. So now I'm going to move on and talk about the key results that the authors provide, right? So this includes the methodology and evaluation. So the methodology that the authors use is sort of pretty standard with these architecture style papers. So they use a simulator to evaluate everything. So it simulates a multi-core CPU that does out-of-order processing. And they assume that the last level cache has 1 megabyte per core, right? So papers today typically, I think, assume a little bit larger values, maybe 2 megabytes or so. But it's still a very reasonable configuration, right? To simulate DRAM, they use a cycle-accurate DDR3 simulator. And the workloads that they choose are twofold, right? So first, they use 6 copy/initialization intensive applications. And these are sort of applications that the authors identified that use a lot of copy initialization applications. And typically we refer to these as micro benchmarks because they sort of show off specific parts of the proposal, right? The second set of workloads they use are Spec CPU 2006, which is sort of a very standardized benchmark suite, and it's arguably representative of everyday workloads. For performance, they use standard metrics, right? For a single core CPU, it's just instruction throughput. For multi-core, they use weighted speed up, which is just sort of computing the speed up across multiple cores. So here's a quick outline of the 6 different copy initialization workloads that they have. We have initializing a system, so system boot up, a compilation, forking some processes, and so forth, right? So all of these somehow make use of copy and initialization. And so here's a sort of plot showing the copy and initialization utilization of all these different workloads, right? So the y-axis here shows the fraction of memory traffic for each of 0, copy, write, and read. And then the 6 different workloads are shown on the x-axis, right? So we see that out of all these workloads, a significant amount of the memory traffic is actually spent on 0 and copy, right? And so these applications were sort of chosen because they demonstrate this, and we can see how these change with RowClone. But in particular, 3 of these workloads, the boot up, the fork bench, and the shell, they have a very large fraction of 0 and copy initialization. Copy and 0 initialization. And we'll see in particular that this correlates with the sort of benefits that RowClone provides. So now I'm going to quickly show the single core results that are presented in the paper. So here we're showing performance and energy, right? And so performance is in red, memory energy reduction is in blue, and the y-axis shows a comparison to the baseline, which is just sort of our traditional everyday system, right? So here what we see is that indeed the 3 applications we identified before that have a lot of zero initialization and copying have pretty significant benefits in terms of performance and also in terms of energy consumption. The other applications that sort of don't have as much zero and copying, they still benefit quite significantly, right? These are tens of percents we're looking at here. But what we take away from this is that the improvements correlate with the fraction of memory traffic due to copy and initialization, right? Which is very intuitive and it makes sense according to what we'd expect. The second set of results I'm going to present is for multi-core systems. So here, what we notice actually is that the reduced bandwidth consumption benefits all applications, right? So even if only some of the applications on the core have less off-chip memory traffic because we're using RowClone instead of traditional methods, all of the applications on the system will benefit because they're all sharing the memory resource, right? And so the way the authors evaluate this is that they actually run copy and initialization intensive applications, so those 6 workloads we saw before, alongside memory intensive spec applications, right? So it's like, actually what the authors do is half and half, right? Half the cores run the first 6 workloads, the remaining half run spec applications. And so the authors provide evaluation results for 2, 4, and 8 core workloads, right? And so this is the same sort of plot we saw before. And when we look at the performance improvements, we see that the performance improvement actually increases as we increase the number of cores, right? And so this, is sort of due to more contention between all these applications, and all these benefits sort of come together. Second, when we look at the energy improvement, we see that also there's significant improvement for all of these. And while it looks like the energy improvements are decreasing as we get to more cores, it's actually consistent with improving the energy per instruction, right? So you can imagine with a 4-core workload, we're running twice as many instructions, hand waving a little bit, as the 2-core configuration, and maybe 4 times as many with the 8-core configuration. So if we sort of look at the energy per instruction, it's a net win, right? Okay. So now I'm going to just give a quick summary of all the technical results. So as in summary, so the paper proposes some sort of bulk data copy and initialization mechanism, and the goal here is to reduce unnecessary movement across the memory channel because this degrades performance and energy efficiency. So the authors propose a mechanism called RowClone, actually 3 types of it, right, which performs in DRAM copies at low cost, right? And so essentially the key idea is to move source rows to destination rows by using row buffers rather than the off-chip channel, right? And so this it provides significant latency and energy efficiency benefits. This mechanism is very useful for accelerating common copy on write and bulk zeroing operations, including all sorts of common operations in today's operating systems. And the improvements in performance and energy efficiency are very significant, and they come at very low DRAM chip area overhead, right? Okay, so now I'm going to move on to sort of the analysis, right? So this was the technical content, and we expect it to be approximately 25 to 30 minutes, right, in your talk. Are there any questions about it before I move on? About the mechanism or anything I talked about? Okay, perfect. So I'm going to analyze some of the strengths that I identify in this work, right? So the first is that it's a very simple and novel mechanism to solve what's an important problem, right? Clearly, there were a lot of motivating examples here, and this paper addresses the problem that it addresses allows significant improvements in performance and energy efficiency, right, as the authors demonstrate. RowClone is also very effective at very low hardware overhead, right? So it's very easy to adopt, let's say, because you don't have to do too many changes in order to use RowClone, and it provides all these benefits that I talked about. Also, in general, it's a very intuitive idea, right? So the key idea was just to copy a row from one place to another place in DRAM. And it's honestly a little bit surprising that this work in 2013 is the first one to present this, even though DRAM has been around since the 50s and 60s, let's say. And so if you go read the paper, actually, the authors reference several patents that have been made, before this paper, essentially. And they sort of vaguely hint towards something that's similar to RowClone, but there's not enough detail to sort of put it together into an actual mechanism. And so the authors here sort of took this all together, put it together into a very simple idea, and showed the benefits of this idea, right? And so I believe that's a strength of the work, right? Because it's easy to convey what's happening here. The mechanism itself, again, is very effective, right? It greatly improves performance and efficiency, with some caveats, right? Assuming the data is mapped nicely and the application can make use of this and so forth. But if all of that is true, the mechanism works really well, right? And especially for the data initialization use case, it seems like a clear win, because here we don't need to worry so much about the mapping, right? Especially if inside the DRAM we have these 0 reserved rows in every single subarray. No matter where the data resides, we can just do a 0 initialization using the fast parallel mode. Right, so we don't have to worry too much about using the other RowClone modes. So it's great for that use case. Another thing that is good about the paper, but maybe not so obvious, is that it actually makes the software designer's life much easier. So what happens here is that this sort of opens up a new way to do things in system software, right? Previously, what happens in current systems essentially is that people spend a lot of effort trying to avoid batch copies and batch initializations. Right, so a good example is in operating systems, whenever we fork a process and things like this, we always try and do optimizations like delayed copying, delayed initialization, right? And especially in the virtual machine world, right? So companies like VMware and things like this, they spend a lot of their efforts trying to avoid having to do batch copies when they're initializing different things. And and so forth, right? And so maybe these trade-offs are a little bit different if we have a mechanism like RowClone, which is say, yeah, if these copies are so much faster, how do we actually design the software to not be so concerned about all of these copies that we have to do? Maybe things are a lot more straightforward. So instead of trying to create some crazy optimization to sidestep the copy, we can just do the copy and it's okay. So these are sort of intangible benefits, right? Even as you saw in the paper's evaluation, it's sort of unclear how to evaluate this idea correctly, right? Because the paradigm is that in today's system software, we try and avoid these copies and initializations as much as possible. So there's not many cases to show off this mechanism, right? Because if you look at today's workloads, they don't really make use of it. And so that's why we have to do things like show these micro benchmarks, because these spec workloads don't do too much of this to begin with. However, if we were to have a workload that does make use of this, it could potentially show off the benefits a lot more, right? So it's just a different design space, essentially. Sort of some other things to talk about the paper itself. The paper tackles many of the low-level and system-level issues. So I give an example of, the cache coherence, the address mapping. While the paper doesn't, comprehensively provide solutions for all these, it provides solutions that would work and that they're reasonable for today's systems, right? And so the authors address this, and it's very clear they thought about these issues. The paper is also well-written and insightful. Of course, this is, up for debate potentially, but I think not all papers are so easy to understand as this one. Especially given that the key idea is very simple, it's pretty easy to understand what the authors are doing and what the benefits are, right? And to follow their methodology for how this idea is developed, why it works, and what the evaluation is. So these are all strengths of the work. Okay. So now I'm going to talk a little bit about the weaknesses I identify in this work. So the first weakness, I've tried to order these by what I believe are most important. So the first one is that it requires data to be mapped to the same subarray in order to achieve the greatest benefits. Right? And so this has been a theme throughout this whole presentation, right? If the data is not mapped such that we can use fast parallel mode, you don't get the main benefits, right? And so if this hardly ever happens, potentially RowClone is not all that useful in practice, right? Same thing I just said essentially. And so another thing that the authors don't really talk about in this paper is that what if we have multiple DRAM channels in the system? So back when this paper was published, it was less common to have so many DRAM channels in a given system. But if you look today at let's say a server-style machine that might be in, like Amazon or Microsoft servers or something, we'll have, 48 cores with multiple sockets, and then we'll have, maybe 6 to 8 DRAM channels, each one, actually more than that, right? We might have 6 to 8 memory controllers, each of which has multiple channels. And so essentially we have tons and tons of different DRAM devices in the system. And if we're trying to copy data from one DRAM device to another, we can't use RowClone at all, right? Because RowClone is for copying data within a single DRAM chip, not from one chip to another. And there's actually no way to copy that data without using the DRAM bus, right? So if we have 2 different DRAM channels, in order to move data from one to the other, you have to go through the 2 buses, right? There's just no way around that. Well, unless you can think of some crazy way to do that. But it stands to reason that this is not something that can be done. And so RowClone is potentially not applicable in these types of systems, right? And so now what you need to do is you need to think about when you're designing your application and operating system, do we want to map all of the application's data to just one DRAM chip so that it can be copied back and forth using RowClone? Because then that limits the amount of memory available to the application, right? Or at least for certain memory allocations, maybe we want to do this. So this is sort of a problem that the paper doesn't address, just having multiple DRAM channels in the system. The second major weakness, I think, is that the inter-subarray copy is very inefficient. So if you remember, this is the one where we use the inter-bank copy twice, right? We move the data to one bank, and then we move it back. And that's not great for many reasons, right? Like you're sort of just wasting bandwidth internally. You need to reserve some memory location somewhere in order to copy data and move it back. It's a weakness of the work. The third weakness I identify is that this causes a significant amount of changes in the system stack. So if you remember from when I presented the strengths, I also sort of put this as a strength, right? Because it opens up new system designs. But it's also a weakness, right? Because if you can imagine a conservative system designer, let's say, the designer of an operating system that's been around for decades and they don't want to change how they're doing things because, that would just be a lot of investment for intangible benefits, let's say, they might not be so open to adopting a system like RowClone, right? Where you need to make changes at all levels of the stack, right? So the application needs to sort of be aware, the compiler, the system software, the drivers, the hardware, everything sort of needs to change. And so it's also a weakness of the work. Yes, the end-to-end system design. Okay, so we talked about that. The next weakness I want to talk about is the cache coherence and data reuse, right? So the paper, as I was describing, provides simple solutions for these, but in some sense they're sidestepping the problem, right? By just saying that every time you do this, flush everything. It would work. It's not great. It's not really evaluated. you're sort of just hand-waving the problem, right? So this is a real issue, and it's a very hard problem in general. Like, there are many papers that sort of talk about different ways to do this type of coherence for these systems that are doing processing inside the memory device, and it's not straightforward at all, right? Because it depends on the application's requirements, depends on the amount of data you're moving, what type of coherence you need. There's so many things that go into it. It's a very hard problem. But again, it's a weakness of the work, right? Because it's not clear how this is done, and it sort of prevents you from just adopting this immediately and being like, yes, this is ready to go. Okay, so these were sort of, these weaknesses I talked about are sort of inherent to the idea. There's also weaknesses about the evaluation itself, right? So the evaluation is solely done in simulation, right? So sure, this is fair, and I would argue this is very reasonable because all these changes aren't reasonable to make, right, for just a general research proposal. So we'd actually have to modify the DRAM device, right, which typically involves fabricating a whole new design. And DRAM devices themselves are very proprietary, right? They're highly controlled by these manufacturers. You can't just go find like an example design on the internet and just go fabricate the chip, right? So it's questionable how you might do this in real hardware. And even if you could, it would be a very extensive evaluation just to try and demonstrate something that you can potentially demonstrate with simulation anyway, right? So it would be nice if they did it in real hardware, but it's sort of unclear. And later on, when we get to the discussion, I'll talk a little bit about some other work that tries to do this in real hardware, and it sort of actually does work. So, okay. The second thing is that the evaluation does not consider multi-chip systems. So this goes back to the point I made up here about it does not help if data movement is across DRAM channels. That's sort of what this is saying, right? Multi-chip systems have potentially multiple DRAM channels. And if we want to move data between those, it's not a straightforward process. And finally, are these the best workloads to evaluate? So this is sort of the favorite set of arguments that reviewers use when reviewing proposals. Just attack the evaluation. But we need to keep in mind that this sort of brings us back into the rat holes that Professor Mutlu described, right? We could spend forever talking about this, right? Are these the right workloads? Did they use the right metrics? Is their configuration fair? It doesn't help to go too far down this path, right? Because then we're not really talking about the benefits of the proposal anymore. So these 3 points down here, while they're good to sort of be aware of and point out, we don't need to keep attacking the paper along this line, right? Okay. So now I'm going to talk about the thoughts and ideas. And so this should sort of be different from before, because this is supposed to be my thoughts and ideas, right? About what I think about the work, right? And so I'm going to start with some extensions and follow-up work, right? So what do you see could be done with this, right? So one area that was sort of mentioned in the weakness that we could work on better is, can this work be improved to do a faster inter-subarray copy? So again, just one more time, this is where we do the inter-bank copy twice, right? So that's not great. Is there an easy way we can make changes to maybe enable this? And so the answer is actually yes. There is some follow-up work so this is Kevin Chang. He's actually another student in Professor Mutlu's group who graduated a couple of years back. He graduated anyway. And this was presented in a conference called HPCA 2016. And they propose a mechanism where they make changes within the DRAM device to alter the interconnect between subarrays. And so now you can enable a read from one subarray into another. So you no longer have this problem of doing inter-subarray copies, right? It becomes almost as cheap as the fast parallel mode. Can this be extended to move data at smaller granularities? So one problem with the fast parallel mode was that although it's super fast, it's a row granularity copy, right? And so you can imagine that not every application needs to do massive copies of 4 kilobytes all the time, or maybe it needs to do even bigger copies, right? So if you remember when I explained the interbank copy, we do this in a pipelined manner, copying a byte at a time, right? And so there, the memory controller may be able to orchestrate this at a smaller granularity, so only copy part of a row or something. But this isn't really possible with the other RowClone modes. So the question is, can this be extended somehow to do this? And I think the answer here is it's sort of unclear. Maybe you need design modifications to sort of change how the DRAM works. But yeah, so that's a good question to sort of think about, and it's a potentially good area for follow-up work. The next point I want to mention is that can we have more efficient solutions to these system-level challenges, including the cache coherence, right? So I said that this is sort of a research area of its own, right? This is definitely true. For different systems, they have different requirements, and there's different ways you can implement this cache coherence. And typically we want to do it to minimize the overhead, but the overhead is defined in terms of the application, right? So if the application needs to sort of operate at the CPU the same time as it's operating in DRAM, you have a different sort of system than an application that can, just sort of offload all its computation and just wait for the data to come back, right? So it's a very general problem that's very difficult to address in general, but it's an important one. Also, this data reuse after copy and initialization, this again goes back to the question of when should we do the RowClone. And so the paper sort of, again, sidestepped this issue a bit. They're like, oh, the hardware can use some high-level metrics to make a decision, or maybe the compiler can provide some hints or something. But there's many different ways you could think about doing this. And so this, I think, is another good area for follow-up work if anybody has any ideas, The next question is, can this idea be evaluated on a real system? How? So I mentioned, I referenced this sort of before, that there are some works that try and do this, and I'll mention them in a little bit, actually, where some papers try to do this with a commodity DRAM chip by, not making changes to the hardware, but just operating a device differently, right? So normally we operate DRAM according to specific timings, right? You do the activate, you wait some time, you do a read, you wait some time, you do a different activate, and so forth. If you violate these timings a bit, do something a little bit funky that's not mandated by the specification, you can get some sort of RowClone type operation, and we'll talk about that. And so this is potentially one way we could have evaluated this idea without fabricating a new chip, right? And it's much more easy. It's much easier to do in general. Another good question is, can similar ideas and DRAM properties be used to perform the computation on data? And so this is a kind of interesting one, right? So what happened in RowClone, if you remember when I presented earlier with the capacitors sharing charge with the bit lines, we're moving charge around, right, in certain amounts, and then using that to just overwrite the destination row. However, you could potentially use this charge somehow to do some type of operation, right? And so there's actually follow-up works that try and implement logic operations using this type of approach, right? So they do AND operations, OR operations, NOT, and then build primitives on top of this, right? So something like an adder or a multiplier and something even more complicated. And so there might be a use case for these types of operations, right? So you're doing them in bulk on multiple bits of data at once, which is a much higher degree of parallelism than the CPU can potentially do. And so it's interesting to consider these works that do something like this. The example here that I have is the Ambit paper, which is by the same author as RowClone, actually, this Vivek. He did some follow-up work also in micro, but in 2017, which is 4 years later. And he proposes doing some logic operations in memory, using the same basic principles that this work relied upon, right? And so it's a natural extension of this work. Here are some of the references that I'm talking about. So this is the paper by Kevin Chang, which sort of improves upon this intra-subarray mode. So these references are in the slides. If you want to look at them, they'll be in the slides published online. This is some in-DRAM operations and an OR, which is sort of precursor work to the Ambit that I mentioned. And here's the full-out Ambit work, which is presented in micro. And so you see it's the same author, right, Vivek. So yes, this sort of allows sort of logical completeness inside DRAM, right? So you can implement whatever you want. There's actually even work that extends this beyond DRAM, right? So this particular paper called Pinatubo extends this to taking things beyond DRAM and to non-volatile memories. So Professor Mutlu in the past has talked about phase change memory, right? Which is sort of somewhere in the space between DRAM and a disk, right? It's non-volatile, it's high capacity, but it's not necessarily as fast as DRAM. You can get similar behavior to RowClone actually in these types of memories as well, following the same basic principles. So this is sort of follow-up work that works as well. And then this is the work I talked about that demonstrates RowClone in real DRAM chips. So they call it compute DRAM. And under certain conditions with certain devices, they're able to actually perform a RowClone with a commodity DRAM device by violating these operating timings a little bit. So it's pretty great. So now I'm going to sort of talk about my takeaways from this work. So this is different from the summary that I gave earlier, right? Because the summary is sort of a summary of the technical content, whereas here this takeaway is sort of what I define to be the things that I feel like are most important in this work, and they should naturally lead into the discussion that we give. So some of these key takeaways, right? So first, this is sort of a novel method to accelerate data copy and initialization, right? At the high level, this is sort of the message of the paper. Right? We can do this, and it's very easy to use, it's very effective. And also, we're looking beyond just working in the DRAM, right? So it's a hardware-software cooperative solution, which means you require changes across the stack, but by doing so, we can enable so much more than just focusing on DRAM itself, or just focusing on the system software itself. So this is a good example of where it pays to actually consider the whole system and try and make modifications wherever you need to make them. There's also very good potential for works building on this in order to extend it. And I gave a bunch of different examples of works that sort of extend this idea. There's even more ways to do it, right? It's sort of a general message, right? This work is a substrate that shows you can do something new, and there's many ways you can take advantage of it. And so that's a very important piece of this work. And finally, it's a very easy to read and understand paper. So you're not going to get lost in the details. You'll be able to understand what's going on and build upon this quite easily. So I think these are all great things about this work. Okay. So the last section of your talk will be the open discussion, right? So here I've provided sort of an example of some discussion starters, right? So these are very, very generic discussion starters. They could essentially apply to any work, right? So let's take a look at them. So what are your thoughts on the previous ideas, right? Everything that I presented. Yeah, you could ask this about any paper that you guys will present in class. How practical is this idea? You know, will this problem become bigger? Will the solution become more important? Are any other solutions you can think of even better than this? And is this solution clearly advantageous in some cases, maybe not so advantageous in others, right? So as you can see, you know, this will apply to anything you guys provide. The downside of these types of discussion starters is that they're so broad that potentially it's hard to come up with a response, right? It's essentially like asking, can you think of anything? And so if my goal is to have an open discussion with you, these are good starting points, but you might get a much more responsive audience if you have something more specific to the work, right? Okay, so this would be sort of the last session in your talk, right? And so, yeah, so are there any questions from you guys about how to sort of do this type of example presentation, or any thoughts you have on the idea itself, right? Just at a high level. Yes, go ahead.
So, just a question for the initialization.
Yes.
Why does it need space? Like, you could just have like an operation that says initialize this memory address, and it could be like put up to VDD or put down to ground, and it doesn't need any capacitors.
Right.
That would be something.
Yeah, it would be in some sense like ideal, and you don't have to waste any capacity for it or anything, right? So that's a good question. I think in this case, one of the big goals of the authors was to avoid making changes in the DRAM chip so much. And what you propose would sort of require a bit of change, right? So now you need some way to sort of just take a cell and just immediately write a 0 or a VDD to it, right? And you could do that with, you know, adding a couple of transistors here and there, or adding some logic in order to drive the cell. With commodity DRAM chips as it is, there's no real way to implement that, or at least nobody's been able to come up with a good way. And but yes, in general, I completely agree. It would be an excellent way to initialize memory if you could just do it straight off without having to reserve rows or do a copy operation or anything. I think one of our TAs actually is sort of working on a similar idea. I'm calling you out, Lois. This is you, right? But yeah, so this is sort of a thing that we're exploring, and it sort of requires hardware modifications as it is. And while the modifications are not so big, the problem is that in general, DRAM manufacturers are very, very, very concerned with making modifications to the design, right? So every piece of area that they use should contribute to some market value, right? It should increase the value of the product. And what we're proposing here is a use case that might be good for some people, but not necessarily good for some others. So it might actually be quite hard to convince the manufacturers to adopt this type of design. But absolutely, it's worth considering because, yeah, it could have great benefits, right? Yeah, I mean, if you can think of a great way to implement it, that's fantastic, right? And maybe it's worth looking at. Right. Okay, yeah, go for it.
So when you showed the performance benefits, you showed that copy gives more of a benefit than the 0 initialization.
Yes.
Like it was about twice as much.
Right. That's the fast parallel mode.
I was wondering if you knew why that was, because it seems like, I mean, my thought would be that they would be about the same.
Yeah, that's a good point, actually. Let me go back to that figure. No. It was the one that showed all of these together, right? All 4 of them. Yeah, so I believe it was this figure.
Exactly.
Yeah, so here your observation is that the inter-subarray copy provides so much more benefit than this initialization, even though you would expect it to sort of be the same because you're just copying a row from one to the other. So that's an excellent question. I don't have an answer off the top of my head. Yeah, can you, yeah, go for it.
I would even consider it should be slower when you copy, because the probability that something's in memory when you first initialize it and zero it is much smaller than when you want to copy it over to some other location where you've probably already used it and you might want to just have a copy of that. So you're more likely to actually have it in cache and not have to and actually have to invalidate that part of the cache, then if you just zeros a memory, you probably never use it before.
Right, so it's sort of just all like cold in the cache before you start streaming your zeros to the memory. That could very well be. So all of this is relative to the baseline, right, of like the normal system. And so the normal system in the 0 case is just streaming zeros to the memory, whereas in the copy, it's potentially writing data that's already in the cache to memory, and so you don't have to go fetch that first. Or did I miss your point?
I think you exactly flipped it around.
Okay.
I said or what I meant to say was that it's supposed to be faster when you zero. Because
yes.
You have to invalidate any cache that you have in the CPU. This is probably that you haven't used those adders before, since it's most commonly in memory.
Yeah, that seems very reasonable. So I think, yeah, you could look at the paper. Maybe it has a little more insight about that, but I'm not sure the ground truth off the top of my head. Yeah. Sorry. Go ahead.
You just mentioned that if you zero it, you don't have to invalidate any cache lines, right?
Yeah.
How is it the case if you have a specific block of memory in cache? You very much have to invalidate it if you set it to 0.
Go ahead.
You said you don't have to invalidate a cache line, but if a cache line maps to a block in this specific DRAM address, and you zero it, you have to invalidate the cache line.
Yes, of course. But I said it's more common or more probable that the memory that you zero out is unused, so not in the cache.
Okay.
Yeah, of course, if it is, then you have to zero it.
Yeah, so I think real quick, yeah, so one point is like it really depends on the configuration that they evaluated with, exactly how they did the baseline and how they did the proposal. So yeah, go ahead, please.
I mean, I'm like not quite sure, like, I mean, this is relative to some baseline, but I'd assume that if we zero out your memory, it's also much more likely that you're going to use it like right afterwards. And as you discussed, like it doesn't put it in the cache, right? I assume it's also the case here. Like maybe this like finishing performance is because you like in the baseline benchmarks, whatever, they like the zeroed out memory was used right after for some operations.
Potentially that's the case. I think so. This evaluation is not with the benchmarks though, right? This is just sort of the standalone value of doing this operation alone. So this is why I'm not exactly sure what the evaluation considered without referencing the paper again.
Yeah.
But yes, absolutely. If they did take into account what you described, then yeah, I agree. Yeah, sorry, what? I think, okay, yeah, go ahead, yes.
I just have a basic question about the graphs here. When you
Yes.
say, when you have a 1x, is this actual speed up, or does that just mean it's just as fast as before? Or is it like 2 times as fast? Because you have a 1x speed up.
Yes, so this 1x it's the same. It's the same speed as the baseline operation, right? And so, yes, so in this inter-subarray version, you get no real speed up, but you do get energy consumption improvements. Yes. Yes, so it's like a multiple factor of the baseline, right? Yeah. Yes?
I mean, I'm no electrical engineer, but from what I understand, if you connect 2 lines or 2 rows in the DRAM, you have higher capacitance, so would you need stronger or larger sense amplifiers to be able to cope with the higher capacitance that is on the line? So wouldn't that technically, once again, increase the energy usage in practice? So would you say that the figures are accurate, or would you still have to factor in those larger amplifiers and the higher power consumption? Because it's just simulation, right?
Right, it's just simulation. And I think the answer is that at no point in this proposal do you have 2 rows active at the same time. You only have one, right? So when you activate row A, it's a normal process, but you deactivate it before you activate row B. And so the sense amplifier is just driving row B. And so the amount, there's only one cell connected to the bit line at a time. So it should never be different from the baseline, right? Yeah. Okay. Yes, back there.
If you have in-memory computation, could it maybe be that this is about the same improvement as this one, and then it would make sense to just like focus on in-memory computation in the first place directly instead of first doing that and then maybe realizing that in-memory computation could be used for that as well?
Potentially, I think that's a great point, yes. So this was one of the first sort of works that looked at this type of in-memory computation. And the future work sort of built upon it, right? So at this time, it wasn't such a big thing to just be like, oh, let's just consider all sorts of in-memory computation types. But absolutely, I agree, yes. If anything, this is maybe a stepping stone that's not so valid if you're using actual operations to do things. Yeah, did you have anything in particular in mind? Or was it just like a general statement?
No, it was just a general question.
Okay.
I thought in-memory computation would also probably not use the buffer at the bus.
Yes.
And so it could have maybe the same improvements and also maybe inter-subarray would be less of a problem with in-memory computation then?
That's right. Yeah, I think when you consider general in-memory computation, there's so many different architectures you could have. Most of them make much more significant changes to the DRAM chip. So a huge value of this proposal is that it's almost one-to-one compatible with current DRAM. And as soon as you have more arbitrary computations that don't use a row buffer and so forth, they usually require a lot more changes. It's not just normal DRAM. So yeah, I guess there's just different trade-offs, right?
But I think it's not just less hardware changes, but you have to change the whole software. And when you then directly use memory computation, you have to do it again. So that could also be an overhead.
Yeah, that's fair. Yeah, it's something that we didn't really talk about much, right? Yeah, I agree. Yes. Anything else?
Wouldn't you say, as you've mentioned before, the implementation would basically contaminate the system stack across the whole stack?
Mm-hmm.
Wouldn't you say that this would introduce unpredictable issues basically down the line with new innovations possibly coming up? Because you don't have the perfect segregation.
Yeah, so sort of the changes that you make for this particular proposal might not be the best changes for sort of future things that come after that. Yeah, I think absolutely. That's definitely something to take into account in the cost of making all these changes, right? Yeah, you could imagine doing it in a more generic way, right? Like providing support for some general primitive that operates on bulk data. And this is just like one such instance of that. And you could imagine other in-memory computation proposals or something sort of fitting into the same framework. But yeah, I absolutely agree. Like anytime you adopt like a very specific thing that does like one thing and one thing well, you're sort of specifying to it a little bit too, right? So I think that's a very general question. And the thing is like this space is so wide open right now. Like there's not like, production systems that are sort of turning out in-memory computation designs. So you're free to propose whatever you want. And so ideally we would have something that's beginning to sort of work with a lot of different proposals rather than just one. I don't know. I think that's what there is to say about it. Yeah. Yes, please.
Is the DRAM row size standardized? Or are they all the same?
Yeah, that's a good question. So it's usually specified in the standard. So this is the DRAM standard. But there's lots of different types of DRAM, right? I mean, if there's DDR3, DDR4, LP, DDR, whatever. So across these different standards, it often changes a little bit. So you might have heard of hybrid memory cube and high bandwidth memory, like some processing memory 3D architectures and whatnot. Usually those use smaller row sizes because the DRAM is broken up into more banks than it is in sort of a DDR type system where DDR4 might have 8 kilobyte rows. So it's somewhat standardized, but it's also somewhat flexible because there's different types of DRAM with different row sizes.
So does that would affect the ISA, right?
Yeah, so this mem copy and mem init proposal, yeah, potentially. I mean, so you could imagine that. So the ISA is just a way to convey intent to the hardware, right? So in the end, the CPU has to go give a signal to the memory controller to issue the appropriate DRAM commands. And so it might do this in a way that if I request a big copy, but the DRAM internally consists of small rows, it would just issue multiple of these rows, right? So you might find a way to do it sort of transparently to the application, to some extent at least. Yeah, does that make sense? I think. Yeah. Okay. Yes. Go ahead.
You mentioned the other paper or the more where they experimented with actually doing this with the DRAM chips. So do you know if they actually had to change the firmware or the memory controller or something, or was it so they just work with equivalent memory chips, or did they actually use the same memory sticks?
Yes, no, that's an excellent question. So the memory sticks themselves are just standard off-the-shelf sticks, but the testing infrastructure was not very conventional, right? So in that paper, they actually used an FPGA-based thing where they can issue custom commands with, because I said that the paper is sort of centered around violating the default specifications for interfacing with the device, right? So with this FPGA thing, they sort of set up their own timings, and they just do it however they want to. A lot of characterization experiments do this type of thing just to show proof of concept. If you've sometimes in standard systems like a laptop or a desktop, the BIOS itself provides you the ability to configure these timings. So a lot of people in gaming do this, right? They change their RAM timings, like a CAS latency and all of that stuff. So it's the same sort of thing. You have some limited programmability sometimes. With the FPGA infrastructure, you can do whatever you want, right? So yeah, there's the question there whether in a commodity CPU would you be able to manipulate these timings. With some of them, yeah, it seems like it, but Those authors, I believe, didn't demonstrate it using like a general, like, you know, a normal CPU system. Yeah. Okay, yeah, go ahead.
Wouldn't it be beneficial to just invalidate the cache line into the checkings in the row, which is the destination, instead of invalidating the whole cache?
Sorry, so I meant to say yes. You invalidate the data in the source and the destination. Yeah, the coherence is just for those. Yeah, not the whole cache.
You only have to invalidate the data of the destination, not of the source.
Yeah, so it's potentially a flush as well, right? Because if the data is dirty, you can't just invalidate, right? You have to flush it. But yeah, only the data that you're operating on. Yeah, absolutely.
Since they proposed changing the ISA already,
Yes.
couldn't you, if you already know that you're zeroing certain memory banks, also do this for the cache? Because you know which data you're zeroing out, and you could theoretically just do the same with the cache.
Yeah, I suppose that's totally fair, yeah. And either use like existing ISA instructions to do that, or just a sort of some hint or something. Yeah, I think that seems reasonable. Yeah, I'm sorry, so back there?
Do you think people would have to change their code all by themselves, or do you think it could be automated in some way? That you could just recompile it and don't have to bother much about it?
Yeah, no, I mean, that's a great question. I think in general, like if the application, so if the programmer can do it, it's sort of ideal, right? Because the programmer knows exactly what he's trying to do, he or she is trying to do. But yeah, I think definitely the compiler could sort of try and automatically detect these things, right? Sort of like, the compiler today like does some auto vectorization and make some SIMD instructions and whatnot. It could potentially do the same thing here. It's just, if the application programmer can actually mandate that this is what it should be, this is when it should be done, then that could be better. But I think both are possible, just depending on what type of software you want to deal with. Yeah, so I think similar things happen with GPU programming, right? So in GPU programming, if you're using like CUDA or OpenCL or one of these languages, oftentimes you specify things like this, right? Like this is the memory that I want to do something specific with. So this could follow some similar programming paradigm as well. Like if you treat this as sort of a way to do specific operations faster, it could be done. Yeah. Yeah, I don't know. I think it's a great idea. Yeah. Sorry. Yeah.
If you have if you want to have two copies of a thing, you don't know yet at which point you want to change something. Will it immediately copy everything, or just as soon as you change something, will make a copy? Because like if you have like 10 rows, and maybe after some time you will only change one row, will it all copy all 10 rows in the beginning, or will it just say like, okay, no, I changed that one row, now I have to copy it? Like at the moment, or is it that it copies all by default?
So I think as the paper proposes it, it's just a row granularity copy, right? So you as the programmer or the compiler or whatever would have to manage that case essentially. Like if you want to keep this set of data together, maybe you'd have to issue multiple of these commands. I mean, I guess it's probably like a natural extension to just sort of have this mem copy, be aware of the rows or something. You can specify more. It just seems like a design decision.
At the moment, if you like clone a virtual machine, will it clone everything immediately, or only when you change one of those virtual machines?
Sorry, that's right. Yeah. So I guess today's systems go through a lot of effort to sort of delay that cloning, right? Okay. In terms of this system, I guess this is where it's kind of unclear, right? So if this row copy is so fast and you have the memory available, then maybe you should just do it immediately. And there's not really much benefit to delaying that copy, because you'll have to pay the copy penalty eventually. But the reasoning behind copy on write as well is also that maybe you don't need those copies, right? And so we're not going to do them unless we actually need them. So in that case, it would be wasteful to just do the copy straight up. So again, I think that's just a design decision based on the trade-offs of doing it now or later. So I don't think there's an easy answer, basically. Yeah. Don't know. Okay. So anyway, I think this is like a good example of what an open discussion would sort of be like. If sort of people don't have too much to say, you can sort of seed the crowd with questions that you've come up with. And so ideally, the discussion starters that you have, you should have thought about them a little bit beforehand and have potential answers ready, right? So I've put up some questions here. If the discussion sort of tapers off, but somebody hasn't talked about something that's an important point to raise, ideally you should have answers sort of prepared to give, and you could stimulate the discussion that way, right? That's always a good way to do things, but it's sort of your space, right? You're able to drive this discussion however you want. It doesn't need to go in any particular direction. And these things are examples in the slides just to help you get started, right? Okay, so yeah, a little lot. So this is the paper, RowClone. You can go look at it if you're interested. Just some quick history on this paper. So Professor Mutlu likes to go over this a lot. So this paper, when it was originally submitted in ISCA 2013, which is, keep in mind, this paper was presented in Micro, right, which is a different conference. So the paper, this is a reviewer's feedback basically on what happened here, right? So the paper's strength, it's well written, and the proposed technique is simple and elegant. So these are some strengths that this reviewer's identified. If we look at the weaknesses, I'm concerned about the applicability of the technique and found the evaluation to be uncompelling in terms of motivating and quantifying the potential benefit, right? Details on how to efficiently manage coherence between the cache hierarchy and DRAM are sort of glossed over, but in my opinion are critical to the narrative, right? So this is sort of nitpicking on details again, and this is sort of a rat hole discussion, right? Everything we talked about, there's a whole side of all these benefits that we have. Addressing each of these problems is a huge issue by itself, and for this reason, this paper ended up being rejected from this conference because of a lot of comments like this. And so I think it's very important to pay attention to how critical you're being on different aspects of the work, right? If you can easily crush something just by focusing on specific parts of it, whereas I think in your strengths and weaknesses and analysis that you give in this course, try and make sure to be pretty holistic about it, what the real benefits are, what you can do with this idea, rather than just attacking it based on what it doesn't do. Okay, so I think that sort of concludes our first example review. And
what do you mean when you say a paper got rejected?
So the process is usually you submit your draft to the conference, and then it goes through a review process, right? So you have several reviewers take a look at it, identify strengths and weaknesses, give feedback, and then in the end they have to come to a discussion. They make a discussion about whether this paper will be accepted in the conference or rejected in the conference. And so
then it will be like presented in a broader space, or what do you mean was accepted, or?
So the conference, typically there's like a date and time for the conference, right? And then so if your paper is accepted, you go present it in the conference, and then it gets published in the literature as the proceedings of the conference, right? So there's sort of like a accompanying mini journal type thing, and so it's considered published. If it gets rejected, then none of this happens, right? So the work is unpublished, and so it's up to you. You modify it, submit it somewhere else, or you sort of understand that the feedback is useful, and you make modifications, or it's up to you at that point. But that's sort of what I mean by accept reject. So here, this was for this conference, ISCA, and so it did not end up being published in ISCA, and so this work was resubmitted to Micro and then ended up published in Micro, right? Okay, yeah. So
These reviews are public?
so no, so when it actually happens in the conference, it's usually in our area at least, it's double blind. So you don't know who the reviewers are, and they don't know who you are. And you just sort of get some feedback, and then you respond to the feedback, and then they make a decision, right? At no point do they actually know who you are, right, as an author. These are not public, right? Nobody really publishes them afterwards. This is an example, of something that happened with Professor Mutlu's paper, so he likes to talk about it a little bit.
The authors get the feedback.
The authors get, yeah, so there's usually several reviewers, and so you might get 4 or 5 reviewers, and you see their feedback, but you don't know who the people giving the feedback are, right? That's the blind process. Yeah, does that make sense?
Yes.
Okay, yeah. All right, so yeah, I'm not sure what to do now. There's not much time left in the class. I could get started on the next thing, or wait, how do you want to do this?
Do you guys have any questions about homework 0 or the paper list?
I have a quick question which isn't related to that, but will the class be graded differently for master students versus bachelor students or not?
No.
Okay.
All the same. Basically, all of you will receive some feedback from the manager during 2 sessions at least. So you will receive the same quality of advising you throughout the semester. So you believe you don't have any problem how to present and what kind of material to cover during the presentation and so on.
That's a good question.
You said we don't immediately start with the presentation.
Yeah, you have 2 weeks from now.
Yeah, in those 2 weeks we still have your lectures, or is that time either for us to work on?
Basically, we can have as this lecture, just examples how to present for other papers, but we will keep you updated.
Yeah, so I think next week will either be more example presentations or I guess there won't be class. I think that's typically what's been done in the past.
As you've just seen, it was a paper that was published or that was rejected from one conference but was rather well written, but the concepts were rather novel. Are the papers that we get, were they all published, or some of them just out of interest, or are some of them rejected papers which are still considered good?
So I think the papers that we have in our list are all papers that have been accepted somewhere at this point. A lot of them are actually very old papers. They're sort of like, which sort of started out the area that they work on. So as far as like whether they were at some point rejected and then accepted somewhere else, I guess we don't really know, right? Typically, like when it gets rejected, you improve it significantly, right? It might even it might look quite different from what you originally submitted. So it's almost like submitting a different paper. Yeah, so I think the ones that we have, do we have any current works in the paper list, or is it all previous published?
Two of them are on archive. Archive is not peer reviewed, meaning that you don't submit it to somewhere where some people will give you feedback. So you can just publish it and that's it. You don't get any feedback on your work. Why we publish an archive? So normally this review process can take like 6 months. So you wait for feedback, you send your correction after the feedback, and you might still reject it after the feedback. So you don't want to wait 6 months to send it to the Word and tell them, I already did this idea. So you can submit it to archive, and meanwhile you can submit it to a conference or journal waiting for the feedback. Hopefully it will get accepted, then it's okay to have both copies there. So there are 2, I think, papers, or at least 2 on the list you have. They are on archive. One of them, I think, it's already old, very old, but received very high number of citations and never get published somewhere else. So they are enough with the archive. And yeah, I forget what's the name of the paper. Yeah, the other one is mine. I'm still publishing it. It's called Sneaky Snake. So yeah, feel free to pick that paper if you like. And yeah, this is how it works. So anyone can submit to archive. It's for free. It's public available, and it's used by different fields.
Okay, sounds good. Yeah. Any other questions about anything really, general course content? Okay. So I think, I don't know, there's not really much time to get into the next example review, so I don't know if we should start on it. What do you think we should do?
Yeah, so normally we have at the end of the semester what we call synthesis report, where you describe what you have learned during the semester, what are the best papers that relevant to computer architecture, bioinformatics, machine learning, or whatever. And from that report, there's one question asking you if you are interested in doing research with our group, as bachelor thesis, semester project, or whatever you like to call it. So you are free always to contact us on Workload 1 on the other side, me. If you are interested in doing a very specific topic, or you don't have idea but you would like to do research, we can assign you to a project. So during the semester, you will see very different topics, medicine to computer architecture, all of them related to architecture then. So if you feel like yourself more attracted to one of these topics, you can, from the weaknesses, you can have some ideas that you'd like to have this weakness or that weakness, or you may not have ideas, as I mentioned, and you'd like just to do something related to that paper. Yeah, just contact us, send us that you are available for this much of hours, and as your CV and so on. And we can assign you to a project and mentor you throughout the next semester. Okay?
Sounds good. Well, okay, yeah. Thanks. Finally, I would just like to apologize for not giving the break. I got too excited about the paper, and I was expecting a bell, but we didn't get a bell, so I just kind of walked right through it.
That's good for you guys. You can leave early.
Yeah. Yeah, so I think then this concludes the lecture for today, and then we'll resume. We'll announce next week what's happening. Perfect. Yeah, thank you.